This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions to the 2019 AP Calculus exam, free response question BC5. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading in Kansas City. And I'll highlight the solutions presented in these guidelines, emphasizing the steps or expressions necessary to earn each point. I'll present the solution to each problem in a little greater detail with more explanation than is given in the scoring guidelines. And even though this was not a calculator active question, I'll show you how to use technology to solve parts of this problem and to visualize results. And because the free response questions are usually very comprehensive, I will suggest some problem extensions. These are additional AP Calculus type questions that involve some of the concepts associated with this question. This free response question involves a family of functions of the form 1 divided by the quantity x squared minus 2x plus k, where k is a constant. In part A, we need to find the value of k such that the slope of the line tangent to the graph of f at x equals 0 is 6. In part B, we assume that k is equal to minus 8, and we need to find or evaluate a specific definite integral. And in part C, for k equal 1, we need to determine whether a certain improper integral converges or diverges. Part A was worth 3 points. Now, to solve this problem, we need to find f prime of x. So the first point was awarded for correct work on the way to finding f prime of x. That is, for a correct denominator in the expression for f prime of x. The second point was for using the denominator to produce a complete correct expression for f prime of x. And the third point was for the answer. That is, for setting f prime of 0 equal to 6 and solving for the value of k. Part B was also worth 3 points. And to solve this problem, we need to rewrite the integrand using partial fractions. So the first point here was for the correct partial fraction decomposition, and this includes finding the value of each constant, a and b. To evaluate the definite integral, the student needs to find two antiderivatives. So the second point was for the correct antiderivatives. And the third point was for the final answer. That is, applying the fundamental theorem of calculus and plugging in the bounds to find a final numerical answer. And remember that a final numerical answer does not need to be simplified. So this expression earns the third point. Part C was worth 3 points. The first point was for recognizing and conveying that this was an improper integral. And this could be presented in a variety of ways. Perhaps the most straightforward approach was to split the original integral at x equal 1 into two separate definite integrals. But somehow here, the student needs to present sufficient evidence of an infinite discontinuity at x equal 1. The second point was for the antiderivative, and the third point was for the answer. The integral diverges, with a sufficient reason. Let's take a closer look at the solutions, and where appropriate, the use of technology to answer these questions. In part A, we need to start by finding f prime of x. Now, I think it's easier to rewrite the expression for f as a power rather than a quotient. Then I can use the power rule and the chain rule to find an expression for f prime of x. We know that the slope of the tangent line of f at x equals 0 is 6. And the slope of the tangent line is the derivative of f. So let's find f prime of 0 and set this equal to 6. Solve for k, and remember we want a value of k that's greater than 0. Here's how I can use technology to solve this problem. Now, I'm going to solve this problem in steps first, as if I was solving it with a piece of paper and a pencil. So, using the TI-Nspire on a calculator page, I first defined the function f. And notice that I used the arbitrary constant k in this definition. I then found the general derivative of f, and then the derivative of f evaluated at x equals 0. Now, using the calculator, I really don't need to find the general derivative first, but I wanted to show you that we can indeed find the symbolic derivative using this technology. Next, I set f prime of 0 equal to 6, and I solved for k. Notice the extra restriction on the value of k at the end of this command. So the TI-Nspire is solving this equation such that k is greater than 0. And finally, I could solve this problem all in one step. Here, I'm solving the equation f prime of 0 equals 6 such that k is greater than 0. And I get the same symbolic answer, by the way, rationalized. I thought it might be nice to visualize this result using technology. I wanted to see a graph of f and this tangent line. So I defined a new function g in the family of f with k equal to 1 divided by the square root of 3. Then I graphed g in an appropriate window, and I added the tangent line to the graph of g at x equals 0. Note that the equation of the tangent line found by the TI-Nspire has slope 6. I think this is a good graphical confirmation that I found the correct value of k. Here's the first of several examples for you to try. Suppose the function g is a member of the family of functions in the free response question, and is defined by this expression. First, find an equation for the tangent line to the graph of g at the value x equals 4. In Part B, sketch a graph of g and the tangent line found in Part A on the same coordinate axes. In Part C, find the value of b where the tangent line found in Part A intersects the x-axis. And finally, find the area of the region bounded by the graph of g, the tangent line found in Part A, and the line x equals b. Hey, that's a cool problem. In Part B of the free response question, we need to evaluate the integral of f from 0 to 1. Now the first step here is to factor the denominator, and then to recognize that in order to find an antiderivative, we can use partial fractions. So we need to find the partial fraction decomposition of the rational function f. Since the denominator is the product of two linear terms, both raised to the first power, the PFD must be in this form, where a and b are constants. To find the constants a and b, write the right-hand side as one fraction with a common denominator, which is the product of the two linear factors. Now we have two fractions that are equal, and their denominators are the same. Therefore, the numerators must be equal. Now, in general, we would have to multiply out the expression on the right and equate coefficients. And this would lead to a set of simultaneous equations. However, here we can find the constants a little easier, with a little finesse. To find a and b in this case, let x equal the root of each linear factor. So first, let x equal 4 in this equation. When x equals 4, we get 1 is equal to a times 6 plus b times 0. So a is equal to 1/6. When x is equal to minus 2, we get 1 is equal to a times 0 plus b times minus 6. So b is equal to minus 1 divided by 6. All right, back to the definite integral. We can rewrite the integrand using the partial fraction decomposition. Next, we integrate term by term. Now, each of these antiderivatives involves a logarithm, and the most general antiderivative here involves an absolute value of both expressions. However, it's really only necessary on the x minus 4 term. X plus 2 is positive on the interval 0 to 1, but x minus 4 is negative on this interval, so the absolute value symbols are necessary. Using the FTC, plug in the bounds and simplify. And I use the property of logarithms to get minus 1 divided by 6 times the log of 2. Here is a way to use technology to solve this problem. Using the TI-Nspire, I first defined the function f. Now I don't need to include this next step, but I wanted to show you a cool feature of the machine, an example of the built-in function expand. I can use this function to find the partial fraction decomposition. Here, the TI-Nspire does all of the work in the background and finds the value of the definite integral. So here's the exact symbolic answer, and that's pretty amazing. Here's another example for you to try. Suppose the function g is another member of the family of functions from the free response question, and is defined by this expression. In part A, find the value of this expression or show that it diverges. And, I like part B, let R be the region in the first quadrant bounded by the graph of G, the x-axis and the y-axis. Find the volume of the solid obtained when R is rotated about the x-axis. In part C of the free response question, we need to consider this definite integral, where the integrand is a member of the given family of functions with k equal to 1. Now the first step here in this solution is to factor the denominator, and then to recognize that because the integrand is undefined at x equal 1, the original integral must be split into two separate integrals, both of which are improper, called type 2 improper integrals in most texts. Now just a reminder, both integrals here must converge for the original integral to converge. If either one diverges, then the original integral diverges. By definition, we need to evaluate each of these integrals by using a one-sided limit. Note that the evaluation here in each case is really a two-step process. We need to find an antiderivative, simplify if possible, and then evaluate the limit. Now, I'm a little uneasy here using the same dummy variable b in each case. Some might misinterpret this somehow as one limit, but this is really two separate problems. The antiderivative of each expression is the same, and is found by using the power rule. And here, I plugged in the bounds and did a little simplification. Now I need to consider each limit separately. I'll take a look at the limit of the first expression. Well, really the part involving minus 1 divided by b minus 1. Now here's how I evaluate this type of limit. As b goes to 1 from the left, the numerator is constant, so it's going to 1. The denominator is going to 0 through small negative numbers, and I represent that behavior with a negative sign in parentheses. So the numerator is constant, 1, and the denominator is getting smaller and smaller negative. So this means the fraction is decreasing without bound, going to minus infinity. And there's a negative sign in front of all of this, so the entire expression is going to plus infinity. So that means that the first integral diverges, and we can stop. The original integral therefore diverges. But just for completeness, let's take a look at the second limit. And really, we just need to consider the limit of this expression. As b goes to 1 from the right, the numerator again is constant, so going to 1, and the denominator is going to 0 through small positive numbers, indicated by a plus sign in parentheses. So this means the entire fraction is getting bigger and bigger, increasing without bound, going to plus infinity. So the second integral diverges also. So finally, both integrals diverge. And since at least one diverges, the original integral diverges. Here's how I can use technology to solve this problem. First, I defined the function f, and then I simply tried to evaluate the given integral. Now, I don't know the algorithm behind the scenes, but I assume that TI-Nspire knows to split this integral, knows there are two improper integrals involved, and evaluates at least one of the improper integrals, and concludes that the answer is infinity. Therefore, the original integral diverges. I also tried to visualize this result on a graph screen. So here's a graph of f, and there's a vertical asymptote at x equal 1. On this graph screen, I tried to evaluate the integral, and the TI-Nspire returned undefined. Now, if I interpret the given definite integral as area under the curve, then the area of this unbounded region, bounded by the graph of f, and the lines x equals 0 and x equals 2, is infinite. Here's one more example for you to try. Suppose the function g is yet another member of the family of functions from the free response question, and is defined by this expression. And a portion of the graph of g is shown in this figure. First, find the value of a such that this limit is infinity. In part b, find the area of the region R. And in part c, find the value of this definite integral or show that it diverges. I hope this video gives you a better idea of how to solve this free response question and how to use technology to solve, visualize, and confirm your results. I think this problem presents some good opportunities to work with improper integrals and partial fractions. And there are some nice conceptual ideas in here also. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.